Welcome everyone to the Rancho Mirage Library and Observatory. My name is Eric McLaughlin. I am the astronomer here, and what we're going to be doing tonight is we're going to be talking about murky subjects. That is, we're going to be discussing nebulae. Now, to actually begin, well, it's worth noting when we're talking about big giant space clouds, well, let's actually talk about seeing things in clouds. It's a worthwhile thing because it's something that we often do. Often people reference seeing bunnies and other things, but since we're in October, it's worth noting some spooky things that can be seen in clouds, including things like a witch's head in this case. Or in another case, I see a really scary looking thing flying in from the side there. It's a wonderful image of a nebula, but what exactly are nebulae is a worthwhile question to ask. And so, well, the word nebula literally is from the Latin, basically meaning a mist, fog, or cloud. It's a worthwhile thing to see. Okay, that's what we're talking about. But what is actually causing these things? Why do we see them? Well, because there's literally stuff out there, typically stuff like gases, such primarily hydrogen and helium, mostly hydrogen, often some dusts, and some high-temperature ionized gases, that is, gases that are having electrons either put into excited orbitals, that is, they are energized, or having electrons completely kicked off. Those interactions can often cause them to emit light. Now, it's worth noting how dense these things are. If you've watched any fun sci-fi movies, good old classic Star Trek and such, you see them fly into nebulae and there's lightning and such, and they're able to hide behind other clouds and such. Well, it's worth noting that the typical density is actually between 100 and 100,000 particles per cubic centimeter. You might say, oh, that's a lot of particles. Well, you compare that to what we have here in this room, and there's 10 to the 19, that is 1 with 19 zeros after it, within 1 square centimeter of this room. So there are absolutely absurdly large numbers of air particles just in this room. And so it's worth noting that despite the fact that these clouds are actually big and able to actually obscure our view, the reason they are able to do so is because they are absolutely vast. Here on the Earth, when we see clouds in the sky, the ones that we actually can expect possibly rain from, not often out here in the desert, but sometimes we can actually get some notable weather from them. Those are much, I can't add enough muches, more dense than what we are looking at in the outer space here. So that said, it's worth noting that there are a variety of different types of nebulae, but there are 5 good categories, though there are some subcategories and other things worth noting that I will also talk about here. The main things to note are emission nebulae, reflection nebulae, dark nebulae, planetary nebulae, and supernova remnants. Those are all worth noting because they all actually represent a variety of different processes that are going on in the universe. Now, most notably, there's some other fun things to note. There are other ways of referring to these things, such as certain things are referred to as H2 regions, which doesn't mean just molecular hydrogen, which in chemistry is referred to as H2. No, in this case, it's actually referring to slightly ionized hydrogen. That is typically little protons going around with their electrons knocked off. So if you hear me use the term H2 region, it is actually somewhat synonymous with an emission nebula, but it's not exactly synonymous. But what is an emission nebula? An emission nebula is actually a big cloud of high temperature ionized gas. Now, typically you have something very bright and very hot to actually put out a lot of energy to actually ionize that material. And what you can often see is bright objects like these stars hanging out right in the center of these types of nebulae, but often there isn't a single center to a nebula like this. It's often very large and diffuse, which I will come back to that term as well. Now, again, when you actually have light emitted from these particular objects, it's when those electrons actually transition closer to the nuclei to a lower energy state, and that process actually emits light. Now, that actual process is very similar to the way neon lights glow. So if you drive down Highway 111 past that car wash and you see an elephant glowing there, that will be a similar process to what we are seeing images of here. Now, that said, it's worth noting why you're seeing a lot of red there, and that red is largely because of hydrogen. Hydrogen and a very specific transition known as an H-alpha transition emits a very specific wavelength of red light. And that is why we actually see a lot of very red nebulae out in outer space. But that is not the only thing worth noting, and other materials will often give other colors and other hues in there. However, it's worth noting some of the images you will be seeing here today will be composites of a variety of different filters. Some of them will be somewhat true to life. Some of them will actually be having specialized filters that actually cause very specific colors to end up in there. So sometimes you'll see things that look a little bit different in color. In this case, this is actually an image I took with our telescope, and it's actually pretty close to what you would expect in real life if you were to actually be able to look at it with eyes clear enough to be able to see the color. Normally, when you look at nebulae with your own eyes, your eyes aren't quite sensitive enough to see the color. All right, that's enough about looking at it, but it's worth noting that in Emission nebulae, that star formation is actually a critical thing in these places. It's something that happens very often, and that's actually how you often get those very big, bright stars, is because they're near where you would expect the center of this big cloud to be, so it's where these biggest, most massive stars form, ending up burning very hot, causing a lot of light to actually be emitted from the surrounding ionized gas. So often it is, again, either ongoing currently or recent, and typically, again, because you find a lot of star formation there, you'll find, astronomically speaking, younger stars, on the order of maybe a few million years old, very young. And one great example is the Orion Nebula, and this one again is the Trifid Nebula, which is this one in particular is towards it's a little bit more towards the center of the Milky Way galaxy, but it's actually still quite close to us, only about 5,200 light years away. Again, fairly close by in astronomical terms. Multiply 5,200 by 10 trillion to get the distance in kilometers, or multiply 5,200 by 6 trillion to get the distance in miles, in case you're thinking on that. All right, moving right along. We have another type of nebula that's worth noting, and that is the reflection nebula, which is really driven by having large clouds of gas that aren't actually being ionized, but they're actually reflecting starlight in a very specific way. And in this case over there, we have a good view of the Pleiades. You can actually see the Pleiades with your own eye. However, spotting the nebulosity requires a very long exposure on a telescope. So normally, if you look through a telescope, you won't be seeing something that looks quite like that, but you will be able to see all of those stars. Now, often, again, a place where there is recent star formation or possibly current star formation. Again, in the case of the Pleiades, which is considered both a reflection nebula, a very faint one, but a more of an open cluster, those stars are all quite young, on the order of, I believe, tens of millions years old, possibly. I have to review that number to give you the exact number. But they are all quite young in astronomical terms. And it is worth noting that reflection nebulas often end up looking a bit blue, and that is worth noting because it's actually fairly similar to the reason why our sky looks blue. There's actually a few different processes, all referred to as scattering. The most famous of that is Rayleigh scattering, which actually favors scattering blue light over red light. It's the reason why our sky is blue, and why when the sun sets, we end up seeing red. We see red towards a sunset because a lot of that blue light has been filtered out by the atmosphere. It's been scattered. So, in a similar fashion here, we can see with reflection nebula that you end up seeing a lot of blue light reflected, but if you were to look through that from the other side, you might see a bit more of a reddish hue to those stars. Now, again, the Pleiades is a classic example of that. And really, you do often see these two types together, emission and reflection nebula. In that previous image of the Trifid Nebula, I intentionally cropped out the reflection nebula above it so you wouldn't get confused. So those two are often found together. And again, this term diffuse nebula is one that is often associated with things like these two, often because they don't have a specific center point or something about which there was a clear origin. And we'll talk more about those type types, but there's another type of nebula that is often referred to as in the category of diffuse nebula, and that is dark nebula. Such as the example here, which we got the Horsehead Nebula, which you can actually say this would be the snout of the horse, this would be the top of its head, and it just looks like a horse's head. Or if you want to continue with the creepy theme of October, this is the head of the monster. He's walking away, and there's one of his arms, and there's another arm there. Yeah, we'll go with that one if we want to be all an October themed. Anyway, this is another type of nebula. It's also referred to as an absorption nebula, and just like the reflection nebula, they consist largely of big clouds of gas, often molecular hydrogen and other things that aren't emitting light themselves. But in this case, they can be sometimes more dense than the reflection nebula, but sometimes it's just a matter of the bright star that is reflecting light is not in front or to the side of them, it is behind it. And as I mentioned with the sunset, if you have some kind of Rayleigh scattering or other scattering, often, or that favors scattering blue light, if you look at an object through that cloud, you'll end up seeing things that are more red-shifted, and this is true of stars you end up seeing as they are partially obscured by dark nebula. So, again, you do often find them near the other diffuse nebulas, and in fact, the Trifid Nebula earlier had a nice dark dust lane, dark cloud right in front of it, actually giving it that sort of three-part shape that gives it its name. Now, these ones are often a little bit smaller in some ways. They're on the order of a few hundred light years across or smaller, but a lot of nebulae are similar in that size as well. And again, the Horsehead Nebula is a classic example of this, as is the Coalsack Nebula. There's also another type that is a good example, and that is Bok Globules, and that raises the question immediately of what are Bok Globules? Well, they're named for a Dr. Bart Bok. You say that 5 times fast, and it'll sound really just plain funny, Bart Bok. But he studied them in the 1940s. In about 1947, he really published a lot on these, and that's what got them really named after them. They are small, they are cold, and they are largely clouds of molecular hydrogen, that is, actual H2, not H2 regions. Again, confusing terms. These are molecules of 2 atoms of hydrogen joined together very frequently. But there are other gases and dusts in them. And again, when I say small, I mean they're about a light year across. In fact, what we're looking at over here, this big old cloud here is actually 2 clouds. You have one cloud there, and the other cloud is actually behind it. Those are about 1.4 light years across, and they tend to have a relatively low mass to them. That low mass may be from a few times the mass of the sun up to tens of times of the mass of the sun, and that sounds like a lot of mass. It is, but it's small in terms of the overall scale of a nebula. That said, when you have systems like these, they are nice and fairly compact, and they can often form multiple star systems. That is, not a star system here, a star system there. Rather, star systems where there are 2 stars orbiting around their common center of mass at the center of that star system, or even more stars all orbiting around each other. So they can actually develop very complicated and interesting star systems from them. This particular set, though, most likely will not, because of those other bright stars you see there. They are actually kind of close by, and the analogy given to these Bok globules is sort of like taking a chunk of butter and dropping it into an extremely hot frying pan. That is what's happening to these Bok globules. They are getting sort of blown away and boiling off, as it were. So in the case of these ones, you may not expect to see stars from them, but you wouldn't expect to be waiting to see stars from them anyway, because that takes millions of years. So let's keep going, though, because there are other types of nebula that are worth noting, such as planetary nebula, such as this one here. This is M57. It is the Ring Nebula, and they are really shells of gas that are expelled from dying stars, stars similar to our sun. But it's worth noting that the name doesn't have to do with there being planets involved with the actual nebula itself. It's actually a note back to the early days of when they were discovered, that they actually sort of looked a bit like planets to some people. There is a planetary nebula that is specifically named the Ghost of Jupiter. So really it's worth noting that these are interesting, very small nebulae. And again, when you actually see about 20 of them appearing spherical in shape, yeah, that makes them even more likely to be confused with planets. However, the Ring Nebula I would not put in that category. It is what is called a bipolar nebula, and it doesn't need a therapist. It is actually just shaped in a very specific way here. In this case, it's actually shaped a bit more like a football with a belt around it. So that football is actually coming out at you and away from us into the or away from us literally, and in this image out the back. So, what is actually going on to actually form these? Well, dying stars, yeah, they are actually very important to actually the next generation of stars, because what has gone on in a star like this is it has actually formed some other elements. It has a bit more helium in it, and it can actually have a little bit of extra carbon and oxygen mixed in, though most of that is actually near the core of that star, and that ends up being left behind at the white dwarf in the center. Now, among the things, though, that you can actually get out of them is a good set of carbon, nitrogen, oxygen, and neon. Those are worth noting because, well, this is a fun note in astronomy. We would typically in astronomy refer to these as metals, and anything above helium is often referred to as metals in astronomy, but it's something I will try not to do. But if you're ever watching something on astronomy or other astronomical things, it's worth noting that if they say metals, they just mean anything not hydrogen or helium. Anyway, but those elements are incredibly important because, yes, without carbon and nitrogen and oxygen and neon and all sorts of other things, we wouldn't be here. So having this type of material actually be expelled from these stars is very, very important to us. So planetary nebula can be very important for that reason. But it's worth actually talking a bit more about how they're actually formed. And the way they're formed is when you have stars like the sun actually growing very old. Again, they actually end up puffing out any outer material, and you end up with things that are on the order of 1 to a few light years across. M57, the previous image, was actually 2.5 light years across. So they actually persist for a bit of time there, and they don't last very long in astronomical terms, from typically only around about a few tens of thousands of years. That is, the previous image with the Ring Nebula, it has been around for about 6,000 to 8,000 years. Come back again in 20,000 years and it'll be gone. So we were very lucky to snap that picture because they don't last very long in astronomical terms. We got there just in time. All right, so when I say stars like the sun, I'm actually referring to lower mass stars, and that seems kind of odd because the sun is absolutely massive, but there are much larger and more massive stars out there. And what happens is a star like the sun, it actually ends up as a white dwarf, meaning the actual core of the star will form a lot of carbon and oxygen in it, and that formation of carbon and oxygen causes the outer layers of that star to get puffed off, giving us that planetary nebula and a very hot, dense core at the center. Now, when it comes to stars that can actually make these things, they're typically referred to as low or intermediate mass stars, again ranging from about 0.8 to 8 times the mass of the sun. This symbol here, this M with the little circle below it, means mass of the sun, so it's a worthwhile thing to note in astronomy. Anyway, but before you get a planetary nebula, you have to get something else, and it's often referred to as a preplanetary nebula or a protoplanetary nebula. I prefer the term preplanetary nebula because protoplanetary nebula can be very confusing because there's another type of object out there referred to as a protoplanetary disk. The protoplanetary nebula has nothing to do with planets. A protoplanetary disk has everything to do with forming planets. So it's worth actually having different terms, so I like preplanetary nebula. Anyway, they are, as I mentioned, the precursors to planetary nebula, and this one again is another very bipolar nebula where you actually have one pole going out this way and one out that way. Now, the reason they're different than planetary nebula is because they are actually more like reflection nebula. They're actually reflecting a lot of the light from their central star. Now, Give it enough time, as that central star becomes significantly hotter, it will actually start getting to a point where it can ionize that gas and turn it into an emission nebula. That is, planetary nebulas are a subcategory of emission nebulas, whereas preplanetary nebulas, hey, back here, preplanetary nebulas are a subcategory of reflection nebulas. So this is what happens to stars like the Sun as they grow nice and old. Stars that are more massive than 8 times the mass of the Sun, give or take a little bit, we're not exactly sure on that cutoff, end up with a supernova explosion. A supernova explosion is what results when you have a very massive star use up all of its fuel. The way a massive star uses up its fuel is it first fuses hydrogen into helium at its core, then it fuses helium into carbon and oxygen, and then there's a whole process of different elements being fused until you end up with a big onion-like of a star that's actually layered with different materials until you fuse iron at the center of that star. And then there's a few different mechanisms that can actually cause that star, this core of that star, to collapse into what is called a neutron star or a black hole, and that process can actually cause something very dramatic, that is a supernova explosion. I'll have a talk specifically on supernova in the future, but we will go over some things here. Again, supernova remnants are what come from the aftermath of those explosions. And as I mentioned, they come from stars that are over 8 times the mass of the Sun, give or take a little bit. And like planetary nebula, they actually are a great source of phenomenal materials to build new worlds with and make sure we're here. So it's good to have these things going on. You just don't want to be right nearby when they go off. All right. And what is worth noting is, yes, these objects, when they actually, when a supernova occurs, it actually puts out enough light to actually compete with all of the other stars in a galaxy combined. This is an enormous amount of light, and in fact, M1 is one of the, well, it is the first supernova remnant discovered because it was actually observed to happen back in I believe it was around 1000 AD, somewhere around that time frame. Chinese astronomers noted a star in the sky that actually was bright enough to persist during the day. It was bright enough to be seen during the day. And give it enough time, fast forward until we actually have observational instruments to be able to look a lot closer, and you get objects like this. Now, the reason it's called M1, for those of you who have heard me talk about Charles Messier, this was an object that Charles Messier got confused with Halley's Comet, and it annoyed him so much he decided to make a catalog of not comets, and this therefore was the first object in his not comet catalog. Hence M1 for his name Messier. Anyway, visible remnants, yes, of this material can actually expand across a number of light years. And going back to this particular object, we know it's a supernova remnant because we were able to not only find a number of things to corroborate its location, but we found an object at its very center. There is a neutron star there, and what's interesting about these objects is we can actually see them change in real time on certain wavelengths. For example, here's a few images from the Hubble Space Telescope. There is a neutron star right about there, and you can actually see what it is doing is actually impacting some of the material around it, causing it to change on astronomical scales in a very short period of time. You can actually see most of this was taken during 2005, 1 year. In contrast, this being one of the first supernova remnants we found, we actually more recently have been watching other supernovae, and a nearby one occurred in 1987 in one of our neighboring dwarf galaxies. In one of the Magellanic Clouds, we had supernova 1987A. Nice and inventive names. So this is the remnant of that particular supernova. It's a very different type of supernova. This one doesn't leave behind a neutron star, and in fact, these type, though they can leave some things behind, they can actually leave absolutely no trace of the object previously. This is what is called a type 1A supernova, and it can leave something behind, but it's complicated. But what we actually have here is a few years later, through only a few years back, we have a nice view of how this particular supernova remnant has changed, and it's actually evolved from being a nice ring to being more of a either Eye of Sauron or a bit of a pearl necklace there. So it's interesting that in the course of a few years, we've actually been able to watch these things evolve and see how they interact with the environment around them. So that is a wonderful thing, but we've gone over so many things, it's worth actually slowing down and taking a look and trying to figure out context and other things. So we've talked about emission nebulae and reflection nebulae and dark nebulae, also known as absorption nebulae, which are all sort of in that category of diffuse nebulae, where we also have Bok globules in the category of dark nebulae. We have planetary nebulae, which, like emission nebulae, can be referred to as H2 regions, where you have that hydrogen being ionized and emitting extra light. And then we also have the note that they are just a special type of emission nebula. Likewise, the preplanetary nebula are just a special type of reflection nebula. And then there's supernova remnants, which can come from various types of supernova. So that's a lot of information. We need to actually put this in some context, and to do that, it's worth asking, what does it all mean? Well, think about it this way. You can actually think about it that these different types of nebulae are really akin to different paints that, when applied to the canvas of context, can really give us pictures which actually describe how the universe functions. That is why it's actually worth going through and actually having this whole spread of different nebulae to talk about and actually try and understand it. So let's try and put it in some context. The good context to actually look at is often a galactic one. This is M51, the Whirlpool galaxy, specifically this part, that is a separate galaxy hiding behind it that is actually interacting with it and likely tugging on it in such a way to actually help spark a lot of star formation. Where would you actually be looking for the nebula here? Well, if you remember, emission nebula are often nice and red in color. So all of these little bright red spots all over here are actually emission nebulae, star-forming regions spread all over this galaxy. Now, it's worth noting that these galaxies, these grand design spiral galaxies as they're often referred to, the spiral arms of them aren't actually formed by this part is always orbiting around at the same rate. It's always going to be this bright. Now, the brightness of these spiral arms is largely driven by a lot of bright young stars. So when you have these bright areas of star formation embedded in these arms, that is there because it is actually, they're in the arms because that is where they're making the bright stars that actually form the arms. Those bright stars are fairly short-lived, and as such, as this density wave propagates around the galaxy, once you get to a point of lower density, the brighter stars actually die off, and you end up with a lot of dimmer stars in between. And then eventually another density wave will roll through this area and cause that gas to get compressed again, that interstellar medium to get compressed again to actually form nebulae again and cause more star formation. So this is a big context of what's going on there, looking at everything. But let's take a look at another big old nebula and talk about everything in context. This is the Carina Nebula. We will not be looking at this from here because it's actually a bit too far south. But by that I mean it's only really visible from the southern hemisphere or closer to the southern hemisphere. But there's a lot of things in just this one image worth talking about. So the next few slides will all be from just this one image. This is a vast region, many light years across. This is a much smaller region where, again, you have some very bright stars and even some Bok globules cast amongst it. You find them all over the place, and you can guess that these ones, yeah, they might be able to form some stars, but looking at all those bright stars around it, they probably won't be lasting very long. Again, astronomical terms. And again, here's some more dark nebulae and a nice sort of scary monster-looking thing here, so good sticking with that October theme here. But this is, again, areas where there's actually a good amount of material where you might be able to have more star formation going on. Likewise, over here, we got some interesting things. You have a nice bow shape over here, where there's a good chance that either this material over here is moving quickly into the other material over there, or the light from the brighter stars on the far side of the screen, or off of the screen, I should say, are actually blowing on this section, causing it to actually get bow-shaped out. That is, the stellar winds actually particles streaming out of those stars are intense enough to actually push this gas back and actually carve it into interesting shapes. And then on the left side of the screen here, we have a funny, really bright star and other things going on there. That is called Eta Carinae. It is a very bright star, and if you look a bit closer, you see something that looks like a giant space peanut, and we can look at that in another way. That is referred to as the Homunculus Nebula, and this is a great view of it where we actually have some 3D models to try and actually describe this object, including what we can't see. But you might be wondering, how do we actually know what it is we can't see? How can we figure out what's going on behind it? Well, there's a lot of ways we can take images and we can learn different things. In this case, there's a particular technique called spectroscopy, and if you use the right wavelengths in spectroscopy, you might be able to peer through some of that gas and see what's going on behind it. Now, I mentioned this is a very bright star, but it's actually two stars. And to tell you more about how this particular nebula formed, I'm actually going to let the NASA scientists who made that 3D model do the talking.
Eta Carinae is one of the most intriguing sources in the sky, and there's actually a large group of us around the world that are keenly interested in it.
Eta Carinae is one of the most massive stars in the galaxy, and it is also a very evolved massive star that we think is near the end of its lifetime. It is believed to be about 90 solar masses, and it was thought to be a single star for the longest time, but it turns out that we know that it is actually a binary system, and there is a second star that we believe to be about 30 solar masses that exists in the system. In the 1840s, Eta Carinae experienced what we call the Great Eruption, where it blew out somewhere between 10 and 40 times the mass of our sun in material. And that material formed this nebula that now surrounds the system.
The nebula itself is a little bit large to map completely by Hubble. And actually we did that a long time ago with the Space Telescope imaging spectrograph. However, we were only able to see evidence of the dusty regions.
So the thing that we did is we had an international collaboration, and we used the Very Large Telescope in Chile to do spectroscopic mapping of the entire Homunculus Nebula. And what makes our mapping unique is that previously only about 5 slits had been used to map the entire homunculus, whereas we use closer to 100 slits across the entire length of the nebula to map everything, including very small details. This is one of the first times we not only have a 3D model for an astrophysical object, but we were actually able to take our 3D model and print it on a 3D printer.
What we find here is that there's dimples in the two lobes, here in the blue shifted, that which is approaching us, and in the red shifted section here. And then most peculiarly, in between, where we might expect to see something fairly symmetrical around here, we see these two wings coming out, tilted both with respect to the bipolar structure and with respect to the orbit of the two stars.
That gives us very important information about the physical mechanisms that are responsible for forming the nebula. For example, trying to determine whether or not it was a single star that had an explosion, or if the binary had some important effect on shaping the nebula.
This new model tells us that potentially the explosive event happened when the stars were closest to each other, and that the material that came out not only came out in the polar regions, but was shaped in the orbital plane, which is between these two systems. It tells us that the explosion event probably started on one side of the star and then propagated elsewhere.
Prior to these observations and the modeling, there was no reason to think that binarity played any role in the eruption or the forming and shaping of the homunculus. But now that we have this more detailed model, it turns out that the distance between each of these features is very similar to measurements that we have of the central binary. And so for the first time, we have evidence that binarity played a role either in the great eruption itself or in shaping the nebula after the initial explosion.
So this is a very unique nebula. It's not like any of the other categories I've already talked about, as it is not a planetary nebula. It's not something that's outpouring of gas at the end of a low-mass star's life. No, this is tens of times the mass of the sun, and it's two objects. So it's a very interesting place, and it's a place we are keenly tracking because who knows when it's actually going to explode. It might anytime soon. And then again, depending on how certain things go, there might be some evidence to suggest that extremely massive stars may not actually go out with an extremely massive supernova. They may actually just collapse. So we're not entirely sure what's going to happen there, so we're keeping our eyes on that particular object. And if you're wondering, yes, I've downloaded the 3D image or 3D model of that nebula. I have not had a chance to put it on our 3D printer yet, so I hope to do that very soon. But when we're actually, again, going through all this, we want to wrap things all together, this whole big view of everything going on. And it's worth noting that when it comes to objects like that, if those two stars, or one of those stars happens to go supernova, and there's all that extra gas around it, well, what can happen when a star goes supernova is it actually can emit a pretty intense shock wave that can actually compress a lot of gas around it and actually drive new star formation. So it's worth noting that the end of another star's life can help bring life to another new set of stars. So it's a worthwhile thing to see there. So we're actually seeing that all of these different processes that go with actually forming stars and forming new solar systems and new star systems and everything actually are fairly well ingrained in nebulae. So when we actually look at the whole chart of how various stars and the life cycle of stars works, nebulae are integral to that. We actually have a nice molecular cloud, a star-forming region being the starting point. You end up with an open cluster, often with a diffuse, very diffuse reflection nebula. In the end, all that gas either being consumed by those stars or blown away. Then you can get a whole variety of stars. Very massive stars will live the shortest lifespan, and then you will actually get them exploding very frequently with what is called a type 2 or other particular subcategories of type 2 supernovae there, or type 1c, depending on specific things. And you end up with that nice supernova remnant up there, and then a remnant of that star as well. More low-mass stars, you end up with stars that will go and inflate to a red giant stage, and again, leave a nice planetary nebula. There's that ring nebula again that we saw earlier. And again, in case you missed it up there, that supernova remnant is, again, M1, the Crab Nebula. But after a planetary nebula is formed, you can end up with a white dwarf, and if that happens to be in a binary system, there are ways to actually drive a type 1a supernova or other types of nova, and you can get other nebulae through those processes as well. So there's all these different things that come together to give a very interesting picture in how nebulae are crucial to understanding how our universe actually produces places like where we are now, and how the actual persistence of various star systems can actually continue on, how you can always have new stars being formed in a galaxy. And so when you look at another picture like this one, look for those bright knots of light in a galaxy, because that is where the next generation of stars are forming and where a lot of wonderful things are going on. So thank you all for being here, and I want to give a special thanks to Ron Treat, who actually helped me with this presentation, and so thank you all for being here as well.